Hi, and welcome to this small lecture in Mechanics of Materials. My name is John Svennegard from VIA University College in Horsens, the Department of Mechanical Engineering. Well, we have this initial problem, which is a cantilevered beam that's completely fixed at point A, subjected to 3 torsional moments. To begin with, I'd like to sketch up a free body diagram for you. So if you just initially sketch up the pipe here with the torsional moment at point D, TD, equal to 18 Newton meters. We have a torsional moment here at point C, TC, equal to 20 Newton meters. We have a torsional moment at point B, equal to 30 Newton meters. And then we're going to apply a positive moment MA or TA at this point, which is the one we need to find. To begin with, we are going to take a summation of torsional moments around the x-axis, positive using the right-hand rule, since we have our coordinate system or main coordinate axis located this direction. That needs to be equal to 0. That means we have the minus 80, we have plus 20, we have minus the 30, and we have plus TA, which needs to be equal to 0. So that yields that TA will be equal to 19 Newton meters. So that's the maximum torsional moment in the beam. Since we can easily check, since in this segment we can see the torsional moment is not changing, so that means it's 80 Newton meters constantly. Then we have it reversed with 20 Newton meters. So that means now we are at 60 Newton meters in this segment between C and B. And in the last segment between B and A, we actually increased the torsion moment with 30 Newton meters. So that means we are at 90 Newton meters. So that's the maximum torsional moment. So let's just index it here, max, on the entire segment of the beam. So now we want to compute the maximum shear stresses on in this tubular section or circular hollow section. So to begin with, we need the polar moment of inertia. We already have the two main parameters given here. So what we do next is calculate the polar moment of inertia, J, which is defined as pi divided by 2 times the radius, the outer radius to the power 4 minus the inner radius to the power 4. So that's actually equal to pi divided by 2 times the outer radius is then obviously 20 to the power of 4, and the inner is then 37 divided by 2, so that's 15 plus 3.5, so that's 18.5 to the power 4. That gives us the polar moment of inertia, which is then equal to 67.3 times 10 to the power of 3 millimeters to the power of 4. So next we're going to use the shear stress formula. So the maximum shear stress is then equal to the torsion applied, torsion moment, times the radius divided with the polar moment of inertia. That means now we can calculate the tau max equal to, we had the TA, which is 19 Newton meters, so that's 19 times 10 to the power of 3 to get it into Newton millimeters, times the radius, and the maximum radius is then obviously 20 divided with the polar moment of inertia, the 67 times 0.3 times 10 to the power 3 millimeters to the power 4. So that gives us tau max to be equal to 26.7 megapascals. Yes, that's the result. So just to sum up what we did is we calculated the maximum torsional moment along the entire cantilevered beam, which is then located between the segment B and A, and then constant in that segment. Then using the polar moment of inertia, we calculated the maximum shear stress, which was then 26.7 megapascals. If we just take a look at the tubular section, then I can try to calculate or show you in a diagram here. If this is then our y-axis, and this is our z-axis, then the shear stress follows a curve that's linear if we are within the linear elastic area. So that means we have the maximum tau max out here on the surface of the pipe, and we have the minimum, which is this level, on the inside of the tube. So that sums up this small example in mechanics of materials. Thank you all for listening.